So we talked about we talked about momentum yesterday, right? Yes. Do you guys feel like you have a decent grasp on momentum and what it is? Okay, good. Because impulse is just going to keep building off of momentum. So today is impulse. This is not like impulse shopping or anything like that. It's a little different, okay? So momentum was mass times velocity, right? Okay, impulse is going to be described as force times an elapsed time. So impulse equals force times delta t. Impulse, force, elapsed time. Perfect timing. Okay. Its units are the same as momentum. So you don't get to escape the kilogram meters per second. We're going to keep them for impulse, okay? And you remember how we had the little arrows over everything for impulse, for momentum, because those vectors? They're still here for impulse too, okay? Because force is a vector, which means that impulse is a vector. So when we were talking about momentum, we said that if velocity was negative, momentum was negative, right? So what do you think happens if force is negative? What's impulse going to be? It's going to be negative too, okay? So this is going to follow suit with that again, just like in momentum. So let's say that we are pushing a shopping cart, okay? And it has a mass of 22 kilograms, okay? And we're going to be applying a force of 6.5 newtons. If we push it over an elapsed time of 1.9 seconds, we need to know what is the impulse going to be. Now, are we given a piece of information that we don't really need? What is it? Yeah, we end up not needing the mass. We just need this force and this elapsed time. So if we know that impulse is equal to force times the elapsed time, we can say that the impulse here would be 6.5 newtons times 1.9 seconds. So what's our impulse going to be here? What did you say it was? Good. And what are the units on that? Kilogram meters per second. Okay? So that's sort of our basis for impulse. Now, if we wanted to solve for force, what would we do with the equation to solve for force? Divide by what? Yeah, we're just going to divide by delta t to get force. And if we want time, what do we do? Divide by force. Okay? Pretty nice, right? Okay. So this is one of the equations for impulse, right? Impulse is also equal to something else, and it's why we teach it hand in hand with momentum. Because the other thing that impulse is equal to is a change in momentum. Okay? So that means we have two equations now. we have impulse equals force times the elapsed time. And we have that impulse is equal to the change in momentum, which means final momentum minus initial momentum. Which means that you need to keep in mind that that means the force times the elapsed time is equal to a change in momentum. So you can use these equations to find impulse, force, change in time, momentums. If you use it to find momentums, it means you can use it to find mass and velocities. It's a lot. So don't worry, we're going to be doing examples together, okay? But they completely interlock, okay? Impulse is change in momentum. What's really cool, you guys, is you remember how earlier in the year we learned that force is equal to mass times acceleration as Newton's second law? So the original way that he wrote it was not that force is equal to mass times acceleration. It actually stems from this equation right here. The original way that Newton's law was formed was that force is equal to the change in momentum over the change in time, which is just this equation rearranged to solve for force, okay? So that was Newton's original law. He actually derived it in terms of momentum instead of mass and acceleration, which is pretty cool, I think. It's fun. So let's do an example together because this is a lot of information. And this is why I wanted to make sure you guys understood momentum before we moved on to impulse. So let's say that we have a force acting on a bicycle. Does anybody in here like to ride bikes? Yeah. Well, it's going to act on this bicycle for 12 seconds, okay? So our delta T is going to be 12 seconds. And the change in momentum is going to be from 15 kilogram meters per second to 38 kilogram meters per second. So that means that our initial momentum is going to be 15 kilogram meters per second, and our final momentum is going to be 38 kilogram meters per second. So the bike's going from this momentum up to this momentum, okay? So does that mean it's speeding up or slowing down? It's speeding up, right? It's got a bigger V for the final. Now, what we want to know is what is the force that's been applied, okay? So do you think we need to start out right away with impulse is equal to force times the change in time, or that impulse is equal to the change in momentum? Yeah, we're going to start out with that it's equal to the change in momentum, okay? So if we know that impulse is equal to the change in momentum, which is the final minus the initial, we can say that the impulse is equal to 38 kilogram meters per second minus 15 kilogram meters per second. So what do we find out that the impulse is? For 38 minus 15. 23. Yeah, 23. Okay, now that we have this, can we solve for our force? Yeah, so that's what we're going to want to bring in, that impulse is equal to force times the change in time. And how do we rearrange this to solve for force? Yeah, we're going to divide by the change in time to get the force. Which means that when we plug it in, we're going to want to do 23 kilogram meters per second divided by our time, or our change in time, which is at 12 seconds. So when we do 23 divided by 12, what do we get as the force that was applied to the bicycle? And what are the units? Newtons. Yeah.
We have done this in Newton's thing.
In what?
Because you showed us the equation, the original Newton's thing. Literally, it's just that.
That's what we did. We did the change of momentum divided by time. Yeah, so it's the exact same thing. It'll just be a different way to write it. But good observation. Good observation. Okay, do you guys have a question about this one? No? All right, let's do another example. All right, so now let's say we are going to deliver an impulse of 12.2 kilogram meters per second, okay? 12.2 kilogram meters per second.
This is an impulse.
This is an impulse. So I equals. And it's delivered to an object whose initial momentum is 4.5 kilogram meters per second, okay? So our initial impulse is 4.5 kilogram meters per second. We want to know what is the object's final momentum. So how do you guys think would be the best way to address this problem?
Momentum, the change in momentum.
Yeah, the change in momentum, right? So we know that impulse is the change in momentum, which is the final momentum minus the initial momentum, right? So impulse equals P final minus P initial. And what are we trying to find? The final, right? So what do we do to get the final by itself? Add what? Yeah, we're going to add the initial potential. So we should be able to take this impulse of 12.2 kilogram meters per second and add to it our initial impulse of 4.5 kilogram meters per second. And it's going to give us a final momentum of what?
16.7.
Good job. 16.7 kilogram meters per second. So that was almost identical to doing just a momentum problem, right? You're just told that it's impulse instead of change in momentum because they're the same thing. All right, let's do a more loaded example then. Sound good? Let's see here. So what this one says is we've got 3 friends, okay? And they are all pushing a stalled car. Have you guys ever been in that situation? God, if you haven't, you're lucky. My car used to break down all the time. This is the first car I've ever had that doesn't break down on like a regular basis. It's so nice. Okay, well, you're pushing it and its driver to a nearby service station because, of course, the driver's lucky. They get to stay in the car and steer it while it's in neutral. They don't have to do the pushing, okay? So we're going to assume that the car rolls without friction on a completely smooth and level road. So we don't have to worry about angles. We don't have to worry about friction, okay? If the car's at rest initially and the 3 students give a combined push of 305 newtons, we want to know what the momentum of the car and driver is after 12 seconds. So let's see. Let's repeat that again. It's at rest initially. What does that mean? What's going to be equal to 0? Our initial velocity, right? It's going to be 0 meters per second because it starts on at rest. And it says that they're using a combined force of 305 newtons. And we want to know the momentum of the car and driver after they've been pushing for 12 seconds. Okay, so with this information, can you guys tell me, first things first, what our initial momentum is? What's it going to be?
Yeah.
It's going to be 0, right? Because momentum is mass times velocity. We don't need to know what the mass is to know that this is going to be 0 because it gets multiplied by 0, right? Okay, so this is going to be 0 kilogram meters per second, which means that it wants the momentum of everything after 12 seconds. So we're looking for the final momentum, which in this case is going to be the same thing as our change in momentum, right? Because we're going from 0 to whatever the final is, which means over the entire time, we'll have changed everything, correct? Because if we said change in momentum is the final minus the initial, we know the initial 0, that means in this case, the change in momentum is just the final momentum. All right? So using this information we have here, we don't have mass. So how are we going to find the change in momentum?
Force times
Yeah, we know that impulse, which is the change in momentum, is equal to force times that change in time. Is everybody following so far? Yeah, I know impulse can feel loaded, okay? So that means that in order to get the result that we want, which is just this right here, what do we need to do with the information we're given? Yeah, we're going to do 305 newtons times 12 seconds. So what do we get as our momentum after 12 seconds?
3,660.
Yeah, 3,660. And what are the units?
Kilograms.
Kilogram meters per second, okay? Now, we're given a mass, okay? And now we're going to say the mass of the car and driver combined is 1,360 kilograms. All right, so we have a mass now, which is nice. And what we want is we want to know what's the final velocity of the car. So how are we going to take this information that we just found and use it to solve for our final velocity of the car? Yeah, so let's look at what you guys, so you know how we said this, right? And that means it's going to be equal to that mass times the final velocity. And we found that it's equal to 3,660 kilogram meters per second. So what we're going to want to do is what Lainey just said. We're going to want to take this and divide it by the mass in order to get a final velocity. So we're saying that momentum, so this is our final momentum, divide by m, and we get velocity. Does that make sense to everybody? Yeah? Okay, cool. So we're going to take that 3,660 kilogram meters per second that we found, and we're going to divide it by 1,360 kilograms. So I'm assuming some of you have already done this. What do we get? 2.69 meters per second.